Problems number from 28 to 30. We have 3 problems in a row which are connected to the same picture. So first problem. We have a simplified model of a bicycle of mass m. Has 2 tires that each comes into contact with the ground at a point. The wheelbase of this bicycle, the distance between the points of contact with the ground is W. And the center of mass of the bicycle is located midway between the tires and the height h above the ground. The bicycle is moving to the right, but slowing down at a constant rate. We can say it's a. Acceleration has a magnitude a. A resistance may be neglectable, ignored. So first case, number 28. Assume that the coefficient of sliding friction between each tires and the ground is mu, and that both tires are skidding, sliding without rotating. Express your answer in terms of W, H, M and G. What is the maximum value of mu so that both tires remains in contact with the ground? So if we have this situation that both tires contact with the ground and the acceleration is a, it's the easiest way to solve this problem to go to frame of reference of this bicycle. If we have a deceleration to the left in this frame, we have effective gravity field A to the right. And in case if both tires are in contact, it means that this tire has a normal force N1 and this N2. This N1 is 0 and this N2 equal to total weight of whole bicycle with the bicyclist. So in this frame of reference we just need to write equation for static equilibrium around point of contact, point of rotation. So maximum possible acceleration could be if we have a sliding case. It means that this force equal mu mg, and this force create a torque around this point equal mu mg h, which is rotating our picture to the right, clockwise. And we have torque created by force of gravity, which is mg multiplied by w over 2, which is going counterclockwise. So from this equation we can find that the maximum possible coefficient of friction equal w over 2h. And if we look at this answers, the correct answer is A. Next problem number 29. We have the same setup. What is the maximum value of A, acceleration A, so that both tires remain in contact with the ground? So now best way to use our original frame of reference in which we have force of friction F1, force of friction F2, and we have normal forces N1 and N2. And we will choose rotation around center of mass to exclude gravity force. So, if you look at this picture, we have three forces which are acting clockwise around center of mass, which is F1, F2 and N1, and the force N2 acting counterclockwise. So first we can write equation F1 plus F2, that's equal MA, and the equation for static rotation we have F1 plus F2 multiplied by H plus N1 multiplied by W over 2, that's equal N2 multiplied by W over 2. So now we can put F1 plus F2 equal MA here. So we have MHA equal N2 minus N1 multiplied by W over 2. And finally we have acceleration A equal N2 minus N1 over M W over 2H. So if you look at this equation, we have N1 minus N2, but we know that N1 plus N2, that's equal mg. So, and it means that maximum acceleration we can get when N1 equals 0. In that case N2 equal mg, and then finally we have wg over 2h. That's answer B. Problem number 30. Assume that both tires are skidding, sliding without rotating. What is the maximum value of A so that both tires remain in contact with the ground? Correct answer is the same as for problem number 29, because in that previous problem it doesn't matter. It was sliding or rotating, so we found the maximum possible acceleration for any condition. So it means that the answer is the same, but we don't see this answer here, so the correct answer is none of them.